So this time, so shall we start? Okay. So it's great. It's my great pleasure to introduce Professor Joel Hamkins, because so he's an old friend of me. So he visited Kobe many years ago, probably 25 years ago. He stayed Kobe about 1 year, and he was a very good friend of me. And so he's now professor at University of Notre Dame, and so he was working at CUNY, City University of New York, for a long time, and he moved to University of Oxford several years ago, and now so he's professor at Notre Dame, and so he's one of the leading mathematician, leading logician in the world, and also he's a very, very good philosopher of mathematics, and he wrote many books about the philosophy of mathematics, and I have a copy of it. And so today, so president of our society was planned to be chair of this talk, but so he is sick in bed now, and so I'm on behalf of the president, so I be a chair of this talk. And today's talk is, the title is the ontology of mathematics. So please, start, Professor Hamkins.
Thank you very much for that introduction. And it's so nice to see you again, Makoto. And I think it was 1998 that I was in Kobe, and it was a formative experience for me. I really loved it so much in Kobe and Japan, and I made so many friends there. And so I'm so glad whenever I can see my Japanese friends again. So thank you very much. It's an honor to be invited. I think I was at the Japanese Association for the Philosophy of Science conference in Tokyo 25 years ago with Makoto, and a bunch of us from Kobe went up there for those talks, and that was extremely interesting to visit in person. So today I'm going to talk about the ontology of mathematics, and please forgive me for speaking in English, and if there's any questions at any point, please just feel free to ask a question, and there'll be some time also at the end for question and discussion. So ontology, what is ontology? It's about existence, and the question is, what does it mean to make existence assertions in mathematics? And in particular, is there an ideal mathematical reality that mathematical assertions are about? Or perhaps there's more than one such universe or reality, or maybe none. And these are the kinds of questions I'm interested in. So in particular, what are mathematical objects? What are numbers or sets or other kinds of mathematical objects? And does every mathematical problem have a definite answer? Or does every mathematical assertion have a definite truth value? These are the questions I'm interested in this talk. And so we'll see what we can say about it. Okay, so what is a number? Well, let's think about the number 57. What is it? What kind of thing is it? Well, of course, this notation 5, 7 is a recipe. It means 5 10s and 7 1s, but we have many other recipes for that same number. For example, 57 is also written in binary like this. And this means 132 and 116 and 18 and no 4s and no 2s and 1 1. That adds up to 32. Or for example, in Roman numerals, we can take 50 and 5 and 2 more, and that's 57. So, so I want to distinguish between the number and the numeral, of course, between the object and the description of that object. The numeral is the description, but the number itself isn't this kind of symbolic or syntactic thing. When I was a child, I read a book called The Phantom Toll Booth. And in that book, it's a fantastic book. I highly recommend it. Numbers come from the number mine deep underground and under the city of Digitopolis. And in the mines, they found the largest number, the biggest one. They announced the largest number had been found. It was a gigantic number 3. It was over 4 meters tall, and it was made of stone. And so, of course, this is a confusion again between number and numeral. It was a big numeral, but not a big number. Broken numbers from the mind were used for fractions. When 5 broke into 3 pieces, you had 5/3. Okay, there's different kinds of numbers, of course. Square numbers are those that can be arranged in the form of a square. And triangular numbers are those that can be arranged in the form of a triangle. And we can have hexagonal numbers and so on. And continuing in that way, maybe one can talk about the palindromic numbers. These are numbers that form a palindrome. So the digits read the same forwards and backwards, like this one is a palindromic, and this is palindromic. Like the phrase, I prefer pi, if you read it backwards, it's the same. But mathematicians often don't like the concept of palindromic numbers because it's not about the number, but about the numeral, because it depends on the base. You can have a palindromic number in one base that isn't palindromic in another base. And in fact, every number is a palindrome. If the base is sufficiently large, then it's just one digit. And so, of course, that's a palindrome. So here's another kind of confounding case. If you think about the fractions 1/2 and 3/6, well, 1/2 is in lowest terms. It's reduced form, but 3/6 is not in lowest terms. But we say that they're equal, they're identical. 1/2 equals 3/6, we'll write it. But how can that be? How can two things be identical if one of them has a property that the other one doesn't have? Right. So again, this is confusing the number with the numeral. The number isn't in lowest terms. It's the numeral, the representation of the number, which is in lowest terms. This number is the same as this number. They're identical. And so being in lowest terms is not a property of the number. So there's a lot of different philosophical attitudes that you can take, and there's many different philosophical positions in the philosophy of mathematics. I'm going to talk about a few of them. Platonism and structuralism and so on. And so all of these different positions have slightly different attitudes towards the nature of mathematical existence assertions and what it means to make an existence assertion in mathematics. So Platonism, of course, according to Platonism, numbers and other mathematical objects exist as abstract objects in a realm of ideal forms. A particular line or circle that you might draw on paper is imperfect. It's not perfectly round. It has imperfections. The line is not perfectly thin. But in the Platonic realm, there are ideal forms, perfect lines, and perfect circles. And also numbers, as well as other mathematical objects, functions, and sets. So according to the philosophy of structuralism, it just doesn't matter what numbers are as individuals. What matters is the structural roles that they play in a system exhibiting an overall structure. That's what matters mathematically for the philosophy of structuralism. So the integer number 0, for example, is the additive identity in the ring of integers. If you have all of the integers and you can add them and multiply them, then 0 is the role that 0 plays, is that it's the additive identity. When you add it to any other integer, you get that integer back. So it's also characterized as the only additive idempotent, the only number z for which z plus z equals z. So there's a lot of different characterizations of the number 0 or of any of other numbers in the integer, in the ordered integer ring. Well, we can have a structuralist account of the natural numbers. If I take the natural numbers as 0, 1, 2, and so on, then Dedekind had identified the following axioms, namely, if we allow ourselves the successor operation, the +1 operation. So 0 is not a successor in this structure. And the successor operation is 1 to 1. So two numbers are equal if and only if they have the same successor. And every number is generated from 0 by successor. One way of saying that is that if you have a set of numbers that contains 0, and is closed under the successor operation, then it must have all the numbers in it. And it turns out to follow from these three axioms all of the familiar arithmetic truths follow as a consequence. So Dedekind proved that on the basis of these axioms, you can make definitions by recursion, and he defined addition and multiplication, exponentiation, and so on, and proved all the familiar facts about those arithmetic operations and arithmetic truths. So this is an extremely powerful axiomatization that settles essentially every question in arithmetic, except those that are engaging with logic and consistency strength issues and so on. Okay. So Dedekind also proved a very important property about his axioms, namely that they were categorical. And what that means is that the axioms determine a unique structure. And this is why I find Dedekind's analysis to be a kind of origin for the philosophy of structuralism, grounded in these categoricity notions. Any two models of Dedekind's arithmetic are isomorphic copies of one another. So if I have two different systems satisfying Dedekind's axioms, so two different zeros and successor operations, then I can kind of match them up. I can match the zero of this one with the zero of the other one, and the successor of zero, I can match them up, and so on. And using Dedekind's theorem on recursion, definitions by recursion, I can use that to extend the matching of these two operations all the way, and it produces an isomorphism of the structures. So this is how one proves categoricity in Dedekind arithmetic. So categoricity, it entitles us to refer to the natural numbers as a unique structure. We don't have to have the natural numbers sort of constructed according to some procedure and then kept in a case in Paris, like the iron bar, the meter bar. We don't have to do that with the natural numbers. If we're structuralists, we can refer directly to the natural numbers by saying, I'm thinking of a structure that satisfies Dedekind's axioms. And that is a successful reference to the natural numbers up to isomorphism, precisely because of the categoricity result. And so this is why categoricity is important for structuralism. It enables us to refer to the mathematical structures that we want to talk about up to isomorphism. So let's talk about the real numbers. Dedekind also observed how every real number is determined by the cut it makes in the rational numbers. If I think about a real number, then it chops the rationals into those below and those above. Actually, Dedekind was thinking about the cut it makes in the real numbers themselves, you know, and what he said was that there's a kind of completeness property. We can imagine that every such cut is filled by a unique real number. If we divide the real numbers into two pieces, such that every number in the lower piece is less than every number in the upper piece, then there will be exactly one real number making that cut. And this is what it means for the reals to be Dedekind complete. And so he postulated that the real numbers are Dedekind complete, because if they weren't, there would be nothing preventing us from filling up the gaps in thought and thus making it continuous. Now, Bertrand Russell mocked him a little bit for this, what he said. So Russell explained how to construct the real numbers using Dedekind cuts in the rationals. So starting with the rational numbers, Russell takes the set of Dedekind cuts in the rationals and defines how to add them and how to multiply them, and proves that that way of building a copy of the real numbers is Dedekind complete. And what he says, this mocking quote, the method of postulating what we want, that's what Dedekind did. He postulated the real numbers are Dedekind complete. Russell says the method of postulating has many advantages. They are the same as the advantages of theft over honest toil. Let us leave them to others and proceed with our honest toil. So what is he talking about? Well, Russell is undertaking the honest toil of placing an ordered field structure on the Dedekind cuts. He's building the real numbers using Dedekind cuts in the rationals. Instead of just assuming the real field is complete, he's constructing an ordered field and proving that it is Dedekind complete. So on this account, a real number is a Dedekind cut in the rational number. So there's an alternative continuity concept provided by Cauchy, inspired by the idea that every real number is the limit of the rational sequences that are converging to it. And Cauchy forms what's called now the Cauchy completion of the rational line using equivalence classes of Cauchy sequences. So we have two different conceptions of what a real number is. So on this account, a real number is an equivalence class of those Cauchy sequences. So Hilbert had identified the natural properties that we want to be true in the real numbers. So in contemporary language, what he specified was that the reals should be a complete ordered field. They should be a Dedekind complete ordered field. And then Huntington proved in 1903 that all complete ordered fields are isomorphic. So this is the categoricity result for the real numbers. It's analogous to Dedekind's result for arithmetic. Huntington gets it for the real numbers. So we're entitled to refer to the real numbers on structuralist grounds by saying, I'm thinking of a complete ordered field, and that is successfully referring. So that's a categorical characterization of the real numbers. So what is the number pi, for example, or another real number that you might like as a mathematical object? What is it? Well, is it a Dedekind cut? Or is it an equivalence class of Cauchy sequences? Or is it a geometric length of some kind, as the ancients took the continuum to be the set of lengths that are possible geometrically? Or is it something else? For the structuralist, it just doesn't matter. This is not the right question to ask. The reals are any complete ordered field, and it doesn't matter which one we use because they're all isomorphic by Huntington's theorem. That's categoricity. Every real number plays a distinct structural role in the real field. If you have a real number, the way that it cuts the rationals is unique for that real number. This is a kind of structural role that every real number plays, and they're all different. So according to structuralism, real numbers are comprehended by their roles within a larger structure. So the structural role played by the square root of 2, for example, in any complete ordered field is that, well, what is the square root of 2? It's a number, it's positive, and it squares to 2, but 2 is the number 1 plus 1, and 1 is the unique multiplicative identity. So we can say exactly what we mean by the square root of 2 in any complete ordered field. So every rational number is definable in such a way, and every real number is characterized by how it cuts the rational line. So what about the complex numbers? Given the real numbers, we want to proceed to the complex numbers motivated by the enticing yet perhaps terrifying square root of -1. So we want to consider complex numbers of the form a plus bi, where a and b are real. Now we said that the imaginary unit I is the square root of -1. People often say that I is the square root of -1. But which one? Because there are two square roots of -1, namely -i also works. If you square -i, then you can factor out the -1. You also get a -1 here. So I and -i are both square roots of -1. And so if you say I is the square root of -1, you haven't really told us which one it is. But there's a deeper problem here, and that is that actually I and -i are automorphic because complex conjugation, which is the mapping of a plus bi sending it to a minus bi, it's swapping the complex plane, turning it upside down. That's an automorphism, an isomorphism of the complex field with itself. And therefore, the number I and the number -i are automorphic images of each other. They're isomorphic copies of each other, and therefore they play exactly the same role in the complex field as far as the field structure is concerned. There is no field theoretic property of I that I has that -i doesn't also have. They have exactly the same properties. There is in principle no way to distinguish them using only the field structure. So is that a problem for structuralism? If one wants to identify numbers with the structural roles that they play in a system, well, then it would seem we'd have to identify I and -i because they play the same role in the complex field. But they're not the same. We don't want to say that they're the same. It's just that the complex field is not a rigid structure because it has automorphisms. Okay, perhaps my I is your minus I, and how would we know? We can't know if we're only talking about the field structure. So, of course, we don't just talk about the field structure when we're talking about the complex numbers, because we think of the complex numbers often as the complex plane, which includes the coordinate structure. So we think about the number a plus bi as a point in the complex plane. And in fact, if we just think about those points in the plane, we can define how to multiply them and how to add them in a way that makes a copy of the complex numbers. And that's one way of seeing that there's nothing so mysterious about the complex numbers after all. But furthermore, the complex plane is interpretable in the real field, not just as a field, but as a field with that extra coordinate structure. And that coordinate structure distinguishes I from minus I. And so the structural role that I and minus I play in the complex plane are different, even though the structural roles that they play in the complex field is the same. Let me relate an allegory. So imagine at your death, you go to heaven and you're astonished to meet God, who informs you, yes, you were completely right about Platonism for the real numbers. There they are. And he points across the way and you see all the real numbers, each of them a perfect Platonic ideal. You find them exactly where you expect to find them. And then God continues, but you were wrong about Platonism for the complex numbers. You have to construct them from the real numbers as pairs with the parentheses and the comma and everything. Okay, now I find this story a bit absurd, because if we would be right about Platonism for the real numbers, then it would seem natural that the complex numbers should be entitled to the same kind of status in the Platonic realm, a real existence, and not only a kind of simulated, interpreted existence. And so, but if that's right, if the ontological status of the real numbers and the complex numbers have a kind of parallelism, well, then of course, we should expect maybe all kinds of different mathematical structures to have a Platonic existence. And this opens the door to what's called plenitudinous Platonism, which I'll talk about a bit later. So let me move now to some set theoretic foundations. And this is based on the curious observation that the categoricity arguments for the natural numbers and for the real numbers take place in set theory. So the natural numbers are characterized by the induction principle. That was the third axiom of Dedekind. But this is an axiom, it's a second order axiom. It's quantifying over arbitrary subsets of the natural numbers. And the real number axiom as a complete ordered field, the completeness axiom, involves arbitrary subsets of the real numbers. Every bounded non-empty set of real numbers has a least upper bound. That's the completeness axiom, basically. That's a second order axiom as well. And people often say, we know what we mean by the natural numbers because we can prove that any two models of Dedekind's axioms are isomorphic. But if that's meant to sort of give us a definiteness about natural numbers, it's relying on set theory, because the axioms themselves are second order and referring to these arbitrary sets of natural numbers. So how can we possibly ground our concept of, say, finite numbers and say we know what we mean by finite numbers if the definition of what that means is referring to this comparatively vague term of arbitrary set of numbers? So maybe that's a problem for structuralism and for Platonism. So how can we secure this definite number concepts upon the comparatively murky concept of arbitrary set? In both cases, we're involving this notion of set. So set theory was initially a tool brought into other mathematical domains. So Dedekind had considered sets of numbers, and Cantor, who really founded the theory, had sets of reals. And gradually, though, the capacity of set theory to express essentially any abstract mathematical structure emerged. And And only then set theory began to serve as a kind of ontological foundation in mathematics. So to be precise in mathematics, in 20th century mathematics, often came to mean to specify one's mathematical structure set theoretically. What is a group? It's a set with a binary operation with some features. What is an order? It's a set with a binary relation having some certain features. What's a field? And so on. What's a topological space? It's a set with a collection of subsets of it having certain features. So we specify our mathematical objects by specifying them in set theory in most of mathematics. Hilbert has this famous quote remarking on this, namely, no one shall cast us from the paradise that Cantor has created for us. So the rise of set theory as a unifying foundation, that foundation I'm talking about, was historically very important because at the time mathematics was diversifying. We had algebra and analysis and geometry and so on, many different subjects of mathematics. But mathematicians often wanted to apply results from one area into another. We would use ideas and theorems from topology and analysis, but use them in algebra or conversely. But that would be logically incoherent if we didn't have a common framework in which all of those subjects live. And set theory provided that common framework, facilitating that kind of practice. So let me focus on the question now, does every mathematical problem have a definite answer? And in particular, does every set theoretic assertion have a definite truth value? So if we think about set theory as a foundation of mathematics, then this question is somehow riding on this one. So the set theoretic universe is built in an iterative sequence of stages. So we start with the elements at the bottom. The elements are the primitive mathematical objects that are not sets, but out of which sets will be formed. So at the next level, we will make sets of elements in all possible ways, and then sets of elements, and sets of elements, and so on, iterating transfinitely. And we get this vast hierarchy, which is the set theoretic universe. Now, set theorists quickly realized that elements were not needed for any mathematical purpose. All of the early set theories were using elements, but in fact, every mathematical structure that arises in set theory can be found isomorphically within the pure sets. The pure sets are the ones that don't have any elements in them, even hereditarily. And so we can sort of recast set theory just with the pure sets. And according to the philosophy of structuralism, the pure sets work just as well as a foundation of mathematics. And that theory is in many respects simpler and more elegant. And so these days, the standard Zermelo-Fraenkel axioms of set theory have only pure sets and there are no elements. So we have this cumulative universe picture of the set theoretic universe. We're starting only with the empty set at the bottom, and then we have the set containing the empty set and the set of all subsets of those things and sets of those and so on. And we iterate transfinitely and get the cumulative universe of all sets. So this universe contains copies of every conceivable mathematical structure. In a sense, the entirety of mathematics can be viewed as existing within this set theoretic universe. So the universe view asserts that there's a unique absolute concept of set, giving rise to the cumulative universe of all sets, just as I described. So the universe view has determinate set theoretic truth and therefore also determinate mathematical truth if one views mathematics as taking place or simulated within set theory. So in that sense, every mathematical question would have a determinate answer in the set theoretic universe. So some support for this universe view is based on consequentialism, on the consequences of the set theoretic axioms. So it turns out a discovery of 20th century set theory is that there are many, many attractive and highly explanatory regularity features, even down low at the level of sets of reals, that follow from the strong set theoretic axioms, particularly from the large cardinal axioms, which are strong axioms of infinity. For example, if you define a set of real numbers using just the usual analytic structure, I mean, addition and multiplication and so on, and allow yourself quantification over integers and over real numbers. If you make a definition of a set of real numbers that way, then it follows from the large cardinal axioms that that set will be Lebesgue measurable. But that's not something that you can prove without these large cardinal axioms. So it's consistent with ZFC without the large cardinal axioms that there would be such projectively definable sets that are not Lebesgue measurable. But if you have the large cardinal axioms, then all of them are Lebesgue measurable. And that's the kind of explanatory regularity feature that I'm talking about. It provides evidence for the truth of those large cardinal axioms. Okay, so the main challenge for this universe view that I've been talking about is what I think of as the central discovery in set theory, which is the enormous range of set theoretic possibility. We have such powerful tools for constructing alternative set theoretic universes. And I'm thinking of tools such as forcing or ultrapowers, canonical inner models, and so on. So much of set theory today is about constructing as many different models of set theory as we can with prescribed properties and detailed relations with other known models. We have thousands and thousands of different set theoretic universes that we can construct using these tools. So let me just mention an example, which maybe some of you have heard of, the continuum hypothesis. So the story begins with Cantor and his theorem that there are multiple different sizes of infinity. So of course, there's the countable infinity of the natural numbers, and Cantor proved that this is strictly smaller than the uncountable infinity of the real numbers. And Cantor asked, is there anything in between those two infinities, between the countable infinity and the uncountable continuum? And the continuum hypothesis is the answer, no, there's nothing in between in size between the natural numbers and the real numbers. That was a major open question since the time of Cantor. It was the Ichiban problem on Hilbert's list of problems at the dawn of the 20th century. It stayed open for decades. Nobody knew the answer to this question for more than 40 years. Kurt Gödel, the great logician, in 1938 proved, though, that the continuum hypothesis is true in what he called the constructible universe, which was one of these artificial set theoretic universes that Gödel had constructed. And then still another few decades later, Paul Cohen, and winning the Fields Medal for this work, proved that there's another artificial model of set theory where the negation of the continuum hypothesis is true. So these two facts together then show that the continuum hypothesis is independent of the axioms of set theory. Neither is provable, it's neither provable nor refutable in the Zermelo-Franco axioms of set theory, the standard axioms of set theory. Now, of course, one could say, well, that's because our axioms are too weak. If they don't settle the continuum hypothesis question, it's because the axioms are too weak. And perhaps we can strengthen the theory to make better axioms that do settle the question. And that becomes a philosophical question then. On what grounds do we extend the axioms? And what would be the reasons for adding new axioms to set theory or their negations? It's not a mathematical question at that point, but rather a philosophical question. So let me imagine an alternative history. So suppose that set theory had proceeded like this. Suppose that theorems were increasingly settled in the base theory, okay? And that, okay, there was an independence phenomenon, but it was limited to paradoxical kind of statements like the Gödel sentence, the self-referential statements. Imagine that independence was just for those kind of strange paradoxical sentences, but that the independence results were settled usually by missing natural axioms. So one can imagine adding an axiom which everyone would immediately agree with as expressing a fundamental truth, and then that axiom settles the independent question, proving it one way or the other. So let's imagine that the basic structure of set theory became increasingly stable and agreed upon. if that is what happened, that would be evidence for the universe view that there's a single set theoretic universe in which all mathematical truth is stable, because we would be converging to it by this whole process. Okay, that's an imaginary history. The actual history is totally different, nothing like that. So the actual history is that we have a vast diversity, a chaotic jumble of set theoretic possibility. So would you like the continuum hypothesis or the negation? Would you also like the negation of the diamond principle? How about 2 to the aleph n equals aleph n plus 2 for every n? Or do you want Suslin trees or Kurepa trees or Martin's axiom? Okay, these are all technical axioms, all of which are independent of the axioms of set theory, and it doesn't matter too much if you're familiar with them or not. I'm just mentioning that we have hundreds and maybe thousands of different kind of statements that are independent of the axioms of set theory. And set theory is all about making all those different combinations happen. We build models to order an enormous diversity of possibility. So there's an amazing fact underlying a lot of those arguments, and that is, imagine that we should build the set theoretic universe, but not with just 2-valued truth, but multi-valued truth, a Boolean algebra of possible truth values. So we will form sets and build the cumulative hierarchy where the set membership relation might have a truth value that's not just true or false, but it could be some element of a truth value element of this Boolean algebra. So if we built the cumulative universe in such a kind of way using multi-valued truth, then the amazing fact is that we can, by picking the right Boolean algebra, we can make the continuum hypothesis come out true, fully true, truth value 1 in the Boolean algebra. Or if we use a different one, a different Boolean value, Boolean algebra, we can make it false. And many of those statements that I mentioned earlier can be affected in their truth value just by building the set theoretic universe with a different multi-valued truth. A different Boolean algebra gives rise to different set theoretic truth. So as a result of all of that diversity of set theoretic possibility, the fundamental object of set theory has become the model of set theory. So we have diverse set theoretic universes. I've written in my multiverse paper, set theory has discovered an entire cosmos of set theoretic universes connected by forcing or large cardinal embeddings, like lines in a constellation filling a dark night sky. So the challenge for the universe view is the view that there's only one set theoretic universe. The challenge is, how can we explain this enormous diversity of set theoretic possibility? So we've constructed all of these artificial set theoretic universes. Will the universalists explain them away as imaginary? It's not enough to just argue that you have a really great theory, a robust theory. Because it's not good enough to just have a really great theory, because we already know about the possibility of all of those other places, all of those other set theoretic universes. And so the universalist has to explain away the pluralistic illusion as an illusion. So, okay, the multiverse view, what I call the multiverse view, is a pluralist view, and it accepts alternative set concepts as fully real. All of those artificial universes are actually real universes, according to the multiverse view. So this is the philosophical position holding there are many set theoretic universes. There are numerous distinct concepts of set, each giving rise to a set theoretic universe. So many of those set concepts are closely enough related to be analyzed together from the perspective of a single set concept. So what might have been purely philosophical, comparing different concepts of set, is in part mathematical, because, for example, the ground model of a model of set theory can analyze the nature of set theoretic truth in the forcing extension. And those are mathematical questions, and yet one can view those as two different or multiple different set theoretic universes. So the subject known as the philosophy of set theory requires a pleasing mix of sometimes quite advanced mathematics, but also philosophical matters. It makes it super interesting, and I invite anyone to join the subject of the philosophy of set theory. Many, many open questions, interesting mathematically and philosophically. So the multiverse view is a kind of realism, namely, the alternative universes can each be taken fully as real as the universe of sets is on the universe view. It used to be years ago when I was a graduate student, that when someone said they were a Platonist, then part of what was meant was the universe view, that there's only one set theoretic universe. But I don't think that's right, and it's not how the word is used today. So you can be a pluralist and a Platonist if you take all those different universes as real. So Platonism should have to do with the real existence of the objects rather than with the uniqueness of the set theoretic universe in which your sets exist. So the situation is that our mathematical tools, and I'm talking about forcing and all those other different construction methods, have allowed us to glimpse into those other mathematical worlds, and that can be taken directly as evidence that they exist in a robust way. So the multiverse view is Platonist, namely Platonism about universes. So the multiverse view has strong affinities with Balaguer's view of plenitudinous Platonism, which I mentioned earlier. He also calls it full-blooded Platonism. And this is from his book called Plenitudinous Platonism. And so the idea is that it's the differences arise from the question how many mathematical objects there are. So full-blooded Platonism can be expressed intuitively as the view all possible mathematical objects exist. Any coherent mathematical theory, for any coherent mathematical theory, there is a mathematical structure that really exists that are the mathematical objects that the theory is about. So I want to make the analogy with geometry. So the geometrical concepts studied since antiquity, points and lines and plane, seemed to have a clear and absolute meaning for millennia. But this view was shattered with the rise of non-Euclidean geometry, where we now have distinct kinds of geometrical universes. At first, of course, geometers would simulate the non-Euclidean geometry inside Euclidean geometry. For example, if you take the sphere and you think of a line as a great circle on the sphere, then you're going to satisfy the axioms of spherical geometry. You know, two of those great circles intersect in a point, and you can make triangles with 3 right angles. If you start at the North Pole and go to the equator and then a quarter of the way around and back up, you've got a triangle with 3 right angles. And so we can simulate non-Euclidean geometry inside Euclidean geometry, or the Poincare disk, and so on. All of those amount to simulations of non-Euclidean geometry inside Euclidean geometry. But in time, geometers accepted the non-Euclidean geometry as its own thing. It didn't have to be simulated inside another geometrical universe. Rather, hyperbolic space is genuinely geometrical all by itself, and it doesn't have to be simulated. And geometers gain intuitions. What is it like to walk around in hyperbolic space? And those geometries are now accepted as fully real and geometrical. There's actually converse simulations of Euclidean geometry inside non-Euclidean geometry. It's a kind of symmetric relation. So the point of this analogy is, why not also in set theory? We have all of these different set theoretic concepts simulated within one another, and we should take them as fully real as we do in geometry. So I want to turn now to what I call the dream solution template for the continuum hypothesis. So set theorists yearn to solve the continuum problem this way. What they want is to produce a new axiom, a natural, obviously true axiom phi. And then they want to prove that this axiom determines this continuum hypothesis. Either it proves it or it proves a negation, one way or the other. So they want to find the missing axiom that settles the continuum hypothesis. Everyone would accept the new natural axiom, and then we would know the answer to CH. This is called the dream solution. This is what everybody would like to see. But I have argued that it's impossible. We will never have that. And the reason my argument is based on the rich experience that we have in worlds with the continuum hypothesis and others with not CH. So it's not just that the continuum hypothesis is formally independent and we don't know anything more than that. Rather, we have built whole set theoretic universes and understood them very deeply in which the continuum hypothesis is true. And we've built other ones where it's false. And we understand what it's like to live in those universes, and they seem fully set theoretic. And therefore, if someone presents an axiom and shows us that it implies CH or that it implies not CH, then we cannot accept it as natural because we already know what it's like in the contrary situation. So the prediction is that any specific dream solution proposal will ultimately be rejected from a position of deep mathematical experience with the contrary situation. It's already happened. Actually, this was the response to Freiling's axiom of symmetry. He proposed a very natural axiom, what he called the axiom of symmetry, and proved that it's equivalent to the negation of the continuum hypothesis. And a lot of set theorists just rejected the axiom as naive. But this is exactly following my prediction. I think that's how it's always going to be. Whenever someone proposes a new axiom that settles CH, then that axiom will never be fully accepted. Of course, it might be very interesting and we will study the axiom and so on. I'm not saying that the axiom itself won't be interesting. I'm saying that it won't be accepted as the final true theory. Finally, we will know the answer because we already know what it's like to have CH and what it's like to have not CH. So this is saying it again. CH is independent, yes, but more than this, because every set theoretic universe has a forcing extension in which the continuum hypothesis holds and another one in which it fails. We can turn it on and off by going to a larger universe. We can make it hold and fail and hold and fail as much as we want. And we understand extremely deeply how to do that. And we therefore have a rich experience in those set theoretic models, and they seem fully set theoretic to us. So it's not just that the continuum hypothesis is formally independent and we have no additional knowledge, but rather we have an extremely informed, deep understanding of how it could be that this continuum hypothesis could be true or how it could fail. And we know how to build these worlds from one another. So if someone proposed an axiom that settled the continuum hypothesis, then we will not look upon it as intrinsic to the concept of set, since we already understand deeply how it could be the opposite. It would be like someone proposing an axiom that implied only Brooklyn exists. But I already know about Manhattan and the other boroughs, the Bronx and Queens. And so I just could never accept an axiom implying that only Brooklyn exists. Okay, similarly, if someone had an axiom that implies CH is true, I could never accept that axiom as the final matter because I already know how CH can fail. So therefore, the dream solution, I argue, will not succeed. So on the multiverse perspective that I'm defending, nevertheless, I claim the continuum question is settled, and it's not correct to describe it as an open question. Sometimes people say the continuum hypothesis is an open question, but I think this is wrong. So the answer to the continuum hypothesis question consists of our detailed understanding in how it both holds and fails throughout the multiverse, how those models are connected to each other, and how we can reach them from each other while preserving or omitting certain features. That's the answer to the continuum hypothesis question. It's true in some universes and false in others, and we can explicate more details about how that works and answer many, many questions about what other things could be true with CH or without it, and so on. Now, of course, there are fascinating further questions about the continuum hypothesis that remain. But the most important central facts are known, and that's what I just described. So, fine. We can't prove that, nor we can neither prove nor refute the continuum hypothesis. It's independent. But still, mathematicians ask, is it true? Okay, but this is, of course, the heart of the issue. So the question seems innocent at first, but interpreting it sensibly leads to those extremely difficult philosophical issues that I have been discussing in this talk. What does it mean to be true? In which universe is it true? Is there only one universe, or are there many? So ultimately, the question becomes, do we have just one mathematical world or many? So that's it. Thank you very much. And I hope that all of you have questions and that we can have a nice discussion. There's references in the slides, and thank you very much.